We're looking at Gcse Physics Unit 1 Higher Tier from Ccea for 2016. And we're looking in particular here at question 6. Part A. Describe in detail the present model of atomic structure known as the Rutherford-Bohr model. In your answer, you should name the particles that make up the atom, their mass, charge, and their location. And you're reminded that in this question you'll be assessed on written communication skills, including the use of specialist science terms. So you might not write it as a table, but this is the information that you're trying to get across, that the proton has a relative mass of 1 unit, a charge of +1, and it's located in the nucleus. The neutron has a mass identical to the protons, more or less. It has no charge, and it's also located in the nucleus. And the electron has much less mass, and the mark scheme particularly mentions this 1/1836 figure, so you might want to learn that off, and a charge of -1, and electrons can be found orbiting the nucleus. The other things that the mark scheme mentions here is that you might want to explain that atoms typically have the same number of protons and electrons that allows them to be electrically neutral. Or you could draw the particles with protons and neutrons in the nucleus and orbiting electrons around the outside. You could draw an atom and give labels for the various parts and information for the various parts. Part B, the Rutherford-Bohr model of the atom is based on the evidence provided by a scattering experiment. The diagram below shows the main features of the apparatus used. Okay, so this is the Rutherford experiment. And you can see we've got 3 basic items. One here is what we need for this, which is a source of alpha particles. So that's an alpha particle source. 2 here is an extremely thin film of gold. Okay, so you've got very thin gold foil here. And over here we have to have some method of detecting the particles. So 1's an alpha source, 2's a very thin gold foil, and 3 is something that will detect alphas. So, I mean, they've drawn a version with an eye looking in, so they would have some kind of scintillation detector here, which would be like a material that produces a tiny flash when an alpha particle hits it. Something like a zinc sulfide screen would produce that, and then you would operate the experiment in a dark room, and a person would be looking for little flashes and using some kind of counter to count how many flashes they had seen. Part 2. Describe briefly how the experiment was carried out. So the detector is placed at a particular position, probably starting at the straight through position. A count is taken over a set period, something like an hour, and then the detectors move to various angles and the process is repeated for those various angles. Okay, so you basically get a count for straight through, 10 degrees off that, 20 degrees off that, all the way round until you're back in the direction that the alpha particles are coming from. So like from 0, which is straight through, to say about 160 degrees or something like that. Okay, so you're positioning the detector at various locations and taking account for a set period. I mentioned an hour there, so count straight throughs for an hour, count number 2 position there for an hour, 3 position, 4 position, 5 position, so that the values are compatible with each other because they were all taken for the same amount of time. Briefly explain the following findings from the experiment. Okay, part 3, that 99.99% of the particles were undeflected. This implies that the atom is, well, you know, there's nothing to hit, that the atom is mostly empty space. That a very small number of the particles bounce back. This implies that the nucleus of an atom is something and something. Okay, now the alphas are positive, so for the nucleus to send them back the way they came, it also has to be positive. Equally, for the atoms to bump off something and go backwards, they have to hit something that's got more mass than them. So the nucleus has to have a positive charge and have lots of mass. And so massive here refers to having lots of mass, not being big. We tend to think of massive as meaning big, but massive means has lots of mass. So it has to be positive to repel them, and it has to be massive in order for them to ping back and head backwards when they bump into it. Part C, the element sodium has the symbol Na. The nucleus of an atom of sodium contains 11 protons and 12 neutrons. Using this information, complete the symbol below. Okay, so we've got 11 protons, 12 neutrons, so that's a total of 23 nucleons and 11 protons. So that's our two numbers. So 23 nucleons, 11 of them protons. Remember, 11 is what gives the material its chemical symbol and its identity, basically. Anything with 11 protons has to be sodium. Part D, the radiation emitted by a substance containing unstable nuclei was recorded over a period of time. The results are shown in the table below. The measurements have not been corrected for background. Just be aware of that. Which did remain constant through the experiment. And so what you're meant to do here is try and think about the idea of background. Okay, so what is background activity? The background activity was measured at 2 counts per second. Using the data shown, determine the half-life of this substance. Remember, the measurements must be corrected for background activity. So first things first is that you need to write in a set of values for corrected counts. Okay, so taking 2 off all of these counts because that's what the background was. So 82 becomes 80, 58 becomes 56, etc., etc. Then we're looking for halving points here. So you can see that there's a halving from 80 to 40, and also there's a halving from 56 to 28. So those are 2 examples of half-lives. So 80 to 40 takes 20 seconds, and 58 to 30 also takes 20 seconds. So that means that the half-life is 20 seconds. So indicate, where you're getting this from. So halving from 80 to 40 takes 20 seconds. Halving from 56 to 28 takes 20 seconds. And then to be really fancy, you're taking a mean of those 2 values to get another 20 seconds. And that's that. Thanks for watching.